Hello and welcome to this video, where we explain the story of stereochemistry and thalidomide. This video will discuss the main events as a story based on the time at which they took place. Starting by the day thalidomide was born. Thalidomide is a drug that was initially introduced in 1957 as a sedative and anti-nausea medication. It was widely marketed and prescribed for various conditions, including morning sickness in pregnant women. It gained significant attention for its perceived safety and effectiveness. At the time of its introduction, thalidomide was considered a breakthrough medication due to its sedative and anti-emetic properties. It was widely prescribed to alleviate symptoms such as insomnia and nausea in both pregnant women and the general population. Thalidomide was marketed under various brand names and became popular in many countries around the world. Years later, around 1960, those pregnant women give birth to babies with severe birth defects. The community was devastated and the affected families were overwhelmed with grief, guilt, and confusion. The babies affected by thalidomide tragedy were born with severe birth defects, which caused lifelong challenges and disabilities. These manifestations included limb malformation. Many babies had limb abnormalities ranging from partial absence of limbs to complete absence, or severe shortening of arms or legs. Facial deformities. Some babies had facial deformities such as a soft lip or plate, malformed ears, or underdeveloped facial structure. These abnormalities affected their appearance and often required surgical interventions for functional and cosmetic improvements. And in around 1961, medical professionals and researchers began investigating the link between thalidomide and these severe birth defects. The first step in investigating the correlation was to gather a comprehensive data on affected infants and their mothers. This involved collecting medical records, conducting interviews with the families, and reviewing available evidence from clinical trials and post-marketing surveillance. By analyzing this data, researchers were able to identify patterns and establish a clear link between thalidomide use during pregnancy and the occurrence of severe birth defects. Experimental studies were also conducted to further understand how thalidomide caused these birth defects. And animal studies played a crucial role in providing insights into the mechanism of thalidomide teratogenic effects. Researchers found that thalidomide interfered with the normal development of limbs and other organs during embryonic growth, leading to abnormal fetal development. The findings confirmed the suspicions. Thalidomide was indeed a teratogenic drug. The conclusive evidence gathered from these investigations led to the immediate withdrawal of thalidomide from the market. After withdrawal of thalidomide in 1966, chemists started going into more details about the chemistry of the drug. During that time, people knew very little about stereochemistry. During the development and protection of thalidomide, it was not initially recognized that the drug exists as two stereoisomers. That was the start of stereochemistry. Introduction of stereochemistry. Stereochemistry is a branch of chemistry that focuses on the three-dimensional arrangement of atoms within the molecules and impact of this arrangement of their chemical and biological properties. It explores the structural difference between the molecules that have the same chemical formula, but it differs in their spatial arrangement. Isomerism is a fundamental concept in stereochemistry. referring to the phenomenon where two or more compounds have the same molecular formula, but they differ in their structural arrangement or spatial orientation. Isomers exhibit distinct physical and chemical properties due to these structural differences. Classification of isomerism. Isomerism can be classified into two main categories: structural isomerism and stereoisomerism. Structural isomerism. Structural isomers have different connectivity or bonding patterns between atoms. Stereoisomerism. Stereoisomers have the same connectivity between atoms but differ in their spatial arrangement. Stereoisomerism arranged from the presence of a chiral center, asymmetric carbon, or a presence of a geometric isomers due to its restricted rotation around double bonds. Stereoisomerism can be further classified into the following subcategories: enantiomerism. Enantiomers are non-superimposable mirror image of each other and exhibit opposite optical activity. They have identical physical and chemical properties, except for their interaction with plane polarized light. For example, R and S enantiomers of a chiral molecule. Diastereomerism. Diastereomers are stereoisomers that are non-mirror image of each other. They have different physical and chemical properties. For example, cis-trans isomerism in alkenes. Now, let's learn about stereochemistry of thalidomide. Thalidomide was originally developed and marketed as a racemic mixture, meaning it contains equal amount of both R-thalidomide and S-thalidomide enantiomers. At the time, it was believed that both enantiomers would have similar properties and effects in the human body. However, this assumption turned out to be tragically incorrect. It was later discovered that while R-thalidomide possessed sedative properties and was responsible for its intended therapeutic effects, S-thalidomide was an enantiomer responsible for devastating teratogenic effects absorbed in newborns. This discovery highlighted the concept of enantioselectivity, which refers to the different biological activities exhibited by enantiomers. This realization underscored the importance of stereochemistry in drug development and safety. It demonstrated that even subtle difference in the spatial arrangement of atoms within a molecule can lead to profound variation in biological activity and toxicity. The thalidomide incident spurred advancement in separation techniques. To ensure accurate identification and separation of thalidomide enantiomers in future products. After continuous researches to understand how this enantiomer works, scientists in 1967 announced that for the R isomer, one proposed mechanism involves its binding to gamma aminobutyric acid, GABA receptors in the central nervous system. By binding to these receptors, R-thalidomide enhanced the inhibitory effects of GABA neurotransmitters, resulting in a sedative, anxiolytic, and muscle-relaxing effects. And for the teratogenic S-thalidomide, one proposed mechanism involved its binding to a specific proteins, such as phosphodiesterase 4, PDE4. Phosphodiesterase 4 is involved in a protein degradation and cellular process. And S-thalidomide has been shown to bind to PDE4, potentially affected its normal function. This interaction may disrupt the regulation of proteins involved in embryogenesis and accelerate the protein binding function, leading to abnormal development. Now, let's see how this drug looks like. Back in the 50s, the teratogenic thalidomide looked like this. And now, Thalidomide is sold under many brand names, including this. Thalidomide is used nowadays for the treatment of multimyeloma, a type of cancer that affects plasma cells in the bone marrow. This is the end of the video. Thank you for watching.